Okay. Good afternoon. This is our lecture. And we return to Combinatorics. Let's start with partitions. So what is a partition? We start from considering a natural number. And we want to represent this number some natural sums. So we want to look at the composition of into some n1, etc. k, where n1, etc. and k is also natural number. The first crucial point is do we look at this decomposition and what decomposition. So called approximation is an unordered one. If the representation of some natural numbers says that we can think about order. It doesn't because is representation of n into some network into some components. And we do not think about the order because that, for example, if you take 5, then 2 plus 3 and 3 plus 2 are the partitions. So we want to care only about them and the symbol of sum.
Can you hear me, Professor?
But second possible
No. Oh my God.
is when we care about the order. This is usually called an order partition or composition. Or sometimes called order partition. Is the same, but we care about the order. The same, but now we care about the order. So say that 2 plus 3 and 3 plus 2 are equal.
Okay. So the first question is how many compositions of n into k summons do we have? So for example, I try to write an example. So if we have, for example, number 7, and we want calculate compositions of 7 into 3 summons, then we have these options. Maybe we have more. I don't know. So we can reorder them, we can state them in a different order. So we have, I suppose, 6 compositions of 1, 2, and 4, 3 here, 3 here, and 3 here. So total it will be 18. But maybe I forget about something. Let me look. Am I? Oh no. But no, not 18, 15. Yeah. So we have now 15 compositions of 7 into 3 summons, and I want you to find the formula of compositions of arbitrary n into k or have k summons. Okay. So let's think about it for a null. I don't know if I need to repeat the definition, but I think it's clear. So we look at natural number n, and we want to represent it as sum of some other natural numbers, and we want to calculate all such number of such decompositions. But there is we have two options here. We can care about the order or don't care about the order. So if we don't care about the order, it's called a partition, and if we care about the order, it's usually called a composition. And now, just for example, I want you to calculate how many compositions of n into k summons do we have. So, for example, if we have 7 into 3 summons, we have 1 plus 2 plus 4, but in different orders we will have 6 such compositions: 1 plus 2 plus 4, 2 plus 1 plus 4, and so on. And for example, if we have 1 plus 3 plus 3, then we can put 1 in the first place and second or third place. So we have exactly 3 compositions. So totally it will be 15 compositions. I just wrote down all possible variations of representation of 7 into 3 summons. And so we have 15 such compositions, and I want you to find the formula for arbitrary n and k. So we can just think about it, maybe ask a question about definition, and then we'll continue. If someone has answer, please write this in chat, or maybe you can just say it. If you have any ideas or maybe suggestions, hypotheses, you can just say it. But if you need me to just write another example, I can do it, of course, if you need. Yeah. So, do you have any suggestions? Okay, so maybe I will have brought an idea, and then you just maybe can finish it. So this is just some combinatoric idea of if you have n. So we have like n balls, and we need to make a k summons. So if we need to k summons, make k summons, then we need to take some delimiters between them. So we need to choose, I suppose, k minus 1 delimiters between them. And so if we have, so we can break them off, and then we take the first part will be the first summon, then the second, and so on. So for example, if we have 7 balls, we can do this and this, and we'll have 2, 3, 2. So this is one decomposition. If we replace them, for example, here and here, we will have 1, 4, 2, and so on. So the question is, how many of possible such pictures? So we just put the 2 delimiters between 7 balls. So how am I? Yeah. So we have exactly. So here we have exactly n minus 1 spaces where we can put these delimiters. And we have exactly k minus 1 delimiters. So we have n minus 1 places for k minus 1 delimiters. And so the answer is n minus 1 choose k minus 1. And if we check, so if we take 7 and 3, then we have 6 choose 2, which is exactly 15. So this is correct. Okay, so this is the correct answer. And if you want to calculate all possible compositions of n, we just need to summarize it over k. And from the combinatorics identity, you know that this is nothing but 2 to the power n minus 1. So we have the formula for the total compositions of n into natural sums. Okay, so maybe I'll just check that you understood correctly. What if we look at the composition not into natural sums, but non-negative sums? How many compositions of n into k non-negative sums do we have? So now, for example, if we have 4 into 3, then we can take 0 as summand. So we took 4 plus 0 plus 0. We can take 3 plus 1 plus 0, 2 plus 2 plus 0, 2 plus 1 plus 1. And I think that's all. We cannot have a composition. If we have 4, we need to choose 0. If we have 3, we need to take 1 and 0. And we have 2 options, 1 to 0 and 1, 1. Okay, so we have 3 compositions of this kind, 6 here, 3 here, and 3 here. And again, we have the answer is 15. But can you just write the formula for this situation? Why is that so? He wrote that the answer is n plus k minus 1, choose k minus 1. Why is that so? Is it correct for this one? Yeah, it's okay. So for example, for this one, we have 4 plus 3 minus 1, 2, 3 minus 1, which is 6 over 2, which is 15. Yeah. Okay, so I just give 2 minutes to think others about it, and then I explain if this is correct answer or no. Yeah, so the idea is the same, but now we have. So what is the difference between this situation and previous? We also have n balls, but now we can place the delimiters. There are several delimiters we can place between the same balls. And so we can put, so we have we can put them before all balls, after all balls. We can put several between the balls, and so it is easier to represent it as we have n plus k minus 1 places, and then we just choose n of them to be balls, and into other k minus 1 we just put the delimiters, and so we will have the composition of kn into k non-negative numbers. So for example, here we have, so we just take 6 possible options, then we choose 2 of them to be delimiters, so for example here and here, and then we wrote 1, 0, 3. And so we can do the same for all possible composition. Okay, so we can calculate we can have the actual formula for the number of decompositions of natural number n into natural sums. But if we ask the same question about partitions, we don't have any actual good formula. So for compositions, we have formula. But for the partitions, we don't have. Because if we forget about order, then we cannot just calculate this using the combinatorial aspects. So, for example, if you have, so how can we calculate the number of partitions? So, for example, we just denote the P of n is the number of partitions. Number of partitions of a number n. So, for example, if you take, P of 5, we just make the list of all possible partitions. So it just be 2 plus 3, 1 plus 4, and 5. For 2 summations, for 3 summations, it will be 1 plus 2 plus 1, 1 plus 1 plus 1 plus 1, 3 plus 1 plus 1. So P of 5 is 7. Maybe I'll do P of 4 is 5. Maybe so if you just look at the first number of partitions, it will have 1, 2, 3, 5, 7, 11, 15, 22, 30, 42, 56, 77. So you have just no we have no formula, we have no linear recurrence relation between them. But some relations we have. So let's just maybe find some of the relations between P of n and some previous number. So if you have, so if you want to write the formula, so if you want to find the let me think. Can we write some? So we don't actually have a problem, because if we, for example, we can say that so for example we want to use the formula for the partitions of n minus 1, but we can draw this, and we say that if partitions have if a partition of n has 1 in them, we can cut this one off, forget about it, and we'll have the partition of n minus 1. But now we need to plus the partitions of n which doesn't have 1 as the summand. And so it is useful to just make some make additional denotations and wrote the summands that the set of the summands of which we construct the partition. So let's just denote it by P of n k1, k2, ks is a number of partitions of n into the summands from the set of k1, k2, etc. ks. It's number of partitions of n into summands k1, k2, etc. ks. So by definition, P of n is P of n 1, 2, 3, etc. n. So now we can write some kind of recurrent formula. So P of n will be what we can use. So maybe I will just write so P of n, if we take the decompositions into 1, 2, etc. k, is so if we take k as summand, then we just can look at the partitions of n minus k into the same kind of summand. Or either we don't have k in there, so we wrote P of n of 1, 2, etc. k minus 1. So we have like this kind of recurrence relation for the partitions. All that we have is that. But it's kind of tricky one because our recurrence relation not only depends on n, but it depends of what are the summands can we take to have these partitions. So this recurrence relations help us to find the number of partitions, but it is not very easy one because if I want to calculate P of 5 of it, I just wrote that either I take 5, so will be 0 of 1 to etc. 5, which is 1 plus P of 5. So the number of partition 5 into summands 1, 2, 3, 4. This will be P of 1 to 3, 4, which is also 1, plus P of 5, 1 to 3, and so on. So we just make this. So we just make this set of summands smaller and smaller, and then we just use the previous indexes, but we need to calculate them, so it is not very easy. So what we can do to calculate this number? What can we say about the number of partitions? Actually, we can just calculate some. So we just can make statements about asymptotics of partitions. So maybe we can just make some kind of different properties about partitions. So let's prove I will just make a statement and then we will discuss it and maybe make another technique to deal with partitions. So I want to prove that the number of partitions of n into k summoned is the same, is equal to the number of partitions of n into summons for which each summon is non-greater than k, where all summons are not less than or equal than k. So if I have additional denotation, and if I wrote like EL of n, k1, ks is the number of partitions of n into L summons, where all summons are from set k1, etc. ks, then the statement is that pk of n, where take all the summons, is equal to p of n 1, 2, etc. k. So for example, if we take I don't know, two summons of 6, so I just need to represent 6 as two summons, which is 5 plus 1, 4 plus 2, and 3 plus 3. Or I can look at all possible partitions of 6 into the summons 1 and 2, which is sum of 6 ones, or I can have 1, 2, yeah, maybe I need to, I just wrote this because I need to check my statement. Yeah, so I need to maybe say, so either I need to take this non-greater than k summons here, or maybe I should take that all summons are not greater than k, but one is actually equal to k. So maybe I will, yeah, so maybe I will change my statement and wrote maybe I wrote like this, so I just wrote that the maximal summand is k. Oh no, sorry. With maximal summand equal to k. So here I need to just write like this one. So I need to take all the summonds that contains k, so I need to subtract the number of partitions of n into letter summons. So we just get rid of this, and we'll have, here we have 3 partitions and here we have 3 partitions. Okay, so I will just again give you like 2 or 3 minutes to think about it. Okay, so maybe I'll give you a hint. Maybe it's not an easy way to prove that they are equal to each other, but I want to write some picture to help demonstrate how get from one to other. So how we can make one-to-one correspondence between them. The picture which I want to write is called Yank Diagram. And if we have any partition n into k1 plus etc plus ks, first of all we can just order this summons because we forget about order, so we can just choose any order as we want, and we can just look at non-increasing or non-decreasing order if we want, and then we just wrote. So there are several possible possible options to illustrate the Yank diagram, and so I just usually use cells for Yank diagrams, but also they use dots, and we can just wrote the upper row to be maximal length, so maybe we can take low row maximal length. So I just wrote them as this picture where we take cells, and then we wrote k1 cells in the first row, k2 cells and into second row, and so on, and ks cells in the last row. So for example, for these guys, maybe I will write the pictures in here, because here I can use color, and some in there I just know why, but I can't. So for example, if we have 5 plus 1, we just wrote 5 cells in the first row and 1 in the second row. For 4 plus 2, we just wrote 4 cells in the first row and 2 in the second. And 3 plus 3 is this guy. Okay, and if we're talking about the second partitions, then we need to write this guy, 1 plus 1 plus 1 plus 2, 2 plus, so if you order them, then 2 will be the maximal number. Then we have 2 plus 2 plus 1 plus 1, which is this Yank diagram. And then we have 2 plus 2 plus 2, which is this Yank diagram. Okay, so maybe we will have a picture. You will get the idea how to get from how we can get one-to-one correspondence between the number of partitions of n into k summons and number of partitions of n in the summons with maximal summand equal to k. Okay, so if you already solved it, I will get another one. Because I want to just maybe now take a little 5-minute break. So I just leave you with this task and give you another one, and you can think about it, and in 5 minutes we'll discuss them. So the second task is how many partitions there where we have non greater than big K summons, and all summons are non greater than big L. So we have a restriction of number of summons and what the actual summons are. So if I use the notation on the other board, we just need to calculate P of 1 of n into 1 to L plus P2 of n into 1 L plus etc. plus Pk of 1 n of 1 L. Or we can just wrote something like P not greater than K n into 1 etc. L. Okay, so just think of these two tasks, and I think we'll have like 5 minutes break right now, and then we'll continue. Yeah, okay, so I think we can continue. Okay, so maybe someone has an idea how to prove the force and maybe has an answer to this. No? No, you can see some relations between them. If you look closely, so you can see that we can make, so this figure is similar to this one, this is some kind similar to this one, and this is some kind similar to this one. Yeah, we just need to make some geometric motion. So we need to make one figure from another, and the idea is just which can make a reflection through the main diagonal. So if we reflect this Yank diagram over this diagonal, we get this one, and vice versa. And the same holds for these guys and these guys. So idea is just that if we take what is partition with K summons? This is the partition where we have exactly K rows. And if we take the diagonal and make a reflection, then we will obtain the diagram which first row has exactly K elements. And then we'll get the diagram with maximal, where the maximal summand is equal to K. And vice versa, if we have the Yank diagram where maximal number is K, it means that first row is the case, have K cells in it. Then if we reflect it over the diagonal, then we will have the diagram which have K rows, which means that it have K summons. So we just take a reflection over the diagonal. Okay, we can call it transposition. It's usually called transposition. So we have take the delta is Yank diagram. Then we can take delta transpose, and we will have the second Yank diagram. Okay. So let's continue. Maybe I'll have like and look into this one. I can give you again, like, I don't know, maybe 2-3 minutes to think about it. So maybe I will give you an example. So we fixed number n, k, and l, and then, or maybe I don't have a restriction of, yeah, I don't have. Yeah, I don't have a restriction of n here. So I can just look at some of from n1 to actually we can have so if we have restrictions of the maximal summand and the number of summons, we can have more than KL, so I think it will be. So for example, if we take K equal 2 and L equal to 3, then we can have, so we have don't have more than 2 summons, no summons are not greater than 3. Then we have 1, 1 plus 1, or 1 plus 2, 1 plus 3, 2, 3. And that's all, yeah? So we don't have more than 2 summons, so we have 1 or 2 summons, and all the summons must be 1 or 2 and 3. Yeah, okay, we can also have 2 plus 2, 2 plus 3, 3 plus 3. So, yeah, that's all, I suppose that's all. So we have fixed number of partitions of this kind of this type is 6. But I want to give, can you give me a formula for arbitrary K and L here? Okay, so what we can do here, so suppose we want to write all possible Yank diagrams in this situation. So let me just write all the pictures. This one, 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 and this one. Yeah, so if we forget about 1, 3, and 3, 1. This one and this one. 1, 2, 3, 4, 5, 6, 7. So I just forget maybe. Yeah. No, there is no. This option is not possible. Yes. So we have 2 rows here, and if we have no more than 3 columns. So what does it mean? So we have this shape. And we want to calculate all Yank diagrams that fits into the shape. So it has no more than 2 rows and no more than 3 columns. And this is maybe reminding you of a similar problem that, so we need to just write the shape of Yank diagram. How many Yank diagrams are fit in this shape? And we can just leave the border of the Yank diagram. So for example, we just start here, finish here, and we go through the border of the Yank diagram. And maybe this reminds you of a similar question. So we just start in the, so we just go only up and right, start into lower left down corner, and we want to get into the up right corner, and we want only right and up. What's the possible number of such routes? Yeah, it's some kind of permutations here. So we want to have 5 steps, and we want 2 of them to be up and 3 of them to be right. Yeah, it's called combination or just binomial coefficient. So we have 5 steps, and we want to take them 2 up and 3 to the right. So we just 5 choose 2 or 5 choose 3. But only one small restriction, but because if we go up and to the right, we will have empty Yank diagram. So if we count them as Yank diagram, then we need to, that is the correct answer. But if we can, if we don't count this, then we can get rid of it, just take the -1. Because this is the one empty, wasn't empty. This is why we have only 9 possible, possible partitions, and here we have 10 minus 1, which is, so we have 10 is bigger by 1. Okay, so we can just calculate some kind of number of partitions, but not what we want. So we cannot get the formula for the P of n, but we can just get some tricky formulas for example, partitions will have restrictions on the number of parts and the number of the value of the sums. The another attempt to say something about partitions and compositions is take about their generation function. And we return into our, again, to our one of our last topic of combinatorics, generating functions. Let's start with compositions. I want not just draw the actual generation functions, but I want to interpret it into the maybe some kind of maybe short form, which can be useful if we restrict our composition. So if we restrict over the same idea, so we just make some different summons, maybe not just all summons, but some subset of the summons, and maybe we want to restrict the number of parts. So I just want to assure that the generation function for the compositions is this one. I just forget which variable do we use. Variable t, yes? Yeah, I suppose when we talk about generation functions. Because I don't know, it's usually use t or x, but I don't remember. So let's look at this. Yeah, maybe I will just get the yeah. So if we take only the natural summons, then we can take this guy. So let's look at this product. Maybe finite one, yes. Just let me think how I can. Yeah, but maybe I will draw this with ones. Oh no. So I just yeah, so maybe I will start with example. So for example, compositions into k summons, we can just write this bracket k times. Why is it so? Because we need to, so we want to T of n, the coefficient before the T of n is the number of compositions of n into k summons. And here I need to just choose the t of k1 from the first bracket, t to the power k2 from the second bracket, t to the power k3 from the third bracket, and so on. T to the power ks, yeah, maybe not k1, k2, k3, yes. L1, L2, L3, Ls. So L1, t to the power L1 from the first bracket, t to the power L2 from the second bracket, and so on, such that L1 plus L2, etc. plus Ls is n, Lk. So if you want to have compositions into K sum, so if we want to take about the generation function for the compositions of partitions, we just take such infinite sums, and if we need to calculate the compositions, we just take the product of them. So similar to that, I want to prove that the generation function for partitions, which we don't have formula for, is this guy. So we just take 1 plus t squared plus t cubed and so on times 1 plus t squared plus t to the fourth plus t to the sixth, etc. times 1 plus t cubed plus t to the sixth power and so on and so on. I want to prove that this is a generation function for the number of partitions. So this is the same as sum of p of n t to the power n from 0 to infinity. Why is that so? So we can, if we look at the partition, if we look at the Yank diagram, we can calculate how many parts are, so how many parts are ones, how many parts of this partition are twos, and so on. So if we have some some partition of n, we just can calculate, we just can rewrite it as L1 times 1, L2 times 2, etc., n times Ln, where L1 is a number of ones here, L2 is number of twos here, and so on. So we just gathered all the same parts together, and then just calculate how much of them do we have. So of course, L1 should be less than n, Ln should be less than 1, L2 should be less than n over 2. And so we can represent this partition into this form. And then, if we have t to the power n, we can just take t to the power L1 from the first bracket, t to the power 2L2 from the second bracket, t to the power n times Ln from the bracket where we start with the power n, and from other parts we should take 1 because the second summand will be already greater than t to the power n. So for example, if I want to just calculate, so this is infinite product of infinite sums, but if I need to calculate the coefficients before the t to the power n, and from the bigger brackets I will take always only 1, and from these brackets I will take only the summands until t to the power n. So this will be the finite product, and so I can calculate this number. So this is a correct definition, correctly defined form of our series. So for example, if I just took the, for example, first all the powers until t cube, then I will have this product, because this is, from other brackets I will take only 1, and then I can so if you want to calculate, so we have 1, here we have only one option here. For the squared, we have options only this and this. And for cube, we have options to take cube from here, to take t cube from here, or take t squared from here and t from here. So we will just the same number of partitions. So t cube corresponds to 1 plus 1 plus 1. T cube here corresponds to partition 3, and t squared here and t is just the 1 plus 2. So we have exactly 3 types of partitions, and we can continue and find the whole generation function. Of course, it is useful. It's this. We can rewrite this maybe in some different form, like the product of all the 1 minus t to the power k, where k change from 1 to infinity. So we just have here many infinities, but here we'll have only one infinity. We just wrote that this is inverse to 1 minus t, this is inverse to 1 minus t squared, this is inverse to 1 minus t cube, and so on. And of course, it is maybe useful because if you need to have some restriction of partitions, because for example, you have partitions where we can sum it only, for example, we don't take 2 as summed. Then we just get rid of this bracket. Or for example, we can have more than 3 ones. Then we can just take the first bracket and forget about this part. So for example, we have tasks like write the generation function for the change in dollar into coins of 1, 2, 5, 10 cents, for example. Then, so if you have, I don't remember how. So we have coins for 5, 2, 5, 10, 25 cents. I don't know. Is it correct? I just don't remember. So if you have these coins for this number of cents, then we want to ask ourselves how many change do we have $1 into this cent. Then we need to just write the generation function, and generation function for the changing n cents into these coins is just this function. So we just take only brackets where we have powers divide. So the multiplicity of the powers of 1, 2, 5, 10, and 25. So all powers divided by 1, divided by 2, divided by 5, divided by 10, and divided by 25. And from this you can just, so if we just try to open the brackets and calculate the coefficients of 10 to the power 100, then we get the number of possible changes of dollars into this set of coins. And also we can use it to prove some tricky identities. So the following task will show you that the number of partitions into pairwise distinct parts are somehow is the same as partitions into the odd parts. So the number of partitions of n into pairwise distinct summands are the same as partitions of n into odd summands. Okay, let me check this for some example. So for example, I don't know, is 9 big enough or maybe we'll have a problem. So when we take start with 7, and if 7 is rather simple, then we go to the 8. So if we take, okay, pairwisely distinct summands, what can we take? 7, 6 plus 1, 5 plus 2, 3 plus 4, 4 plus 2 plus 1. So the summands cannot repeat. Is this all? So the 1 and 2 parts are okay. For 3 parts we have 4 plus 2 plus 1. And the next will be 3 plus 3 plus 1, which is, we have to summon 3 2 times. Okay, let's start to taking them into odd summons. Here we have 7. We have 7 ones. We have 3 and 4 ones. We have 2, 3 and 1, and we have 5 plus 1 plus 1. Okay, we can see that here we have 5 possible partitions, and here we have 5 possible partitions. So, for example, for 7, this true. So the idea, I just want you to try to write the generation functions for the left hand and to the right hand, and just compare them to each other. Maybe we can prove that this is the same generation function, and then we can prove this equality. Yeah. So I just again give you like 5 minutes. Of course, you can ask me if you don't understand the previous stuff, and I need to explain some generation functions, but I think it is not very hard to understand. So just try it yourself, and then if you need help, in 3 or 4 minutes I will just try to write them, maybe left hand sides, maybe right hand sides, and then we compare them. Okay. So if we take about what is this simple. So let's look at the whole generation function for the maybe I will just okay, so what if we have partition into pairwise distinct summands? How can we restrict this formula to have the partitions of n into pairwise distinct summands? Написано, что места английский недостаточно. I know it's a bug maybe, but they're saying that. Yeah. Okay. So if you remember the definition, you can see that what that means. So we have the same summons. If we take more than one summon from bracket, it means that we take like here we have t cube, t squared, t cube, and so on. It means that we take the summons 1, 2 times, 3 times, and so on. And the same holds for every bracket. So this bracket 4 means that we take 2 times 2, and so on. So if we take pairwise distinct, we need to we have the following generation function. And if we take the only odd partitions, odd summons, then we take only the brackets with odd base. So for example, we cannot have this bracket because this contains only how many 2's do we have, and we don't have 2's in, we have odd numbers. So we will have this sum. And so if this is correct, then we need to prove that these derivation functions are the same. And so we just need to write this as, so maybe I will take the first step. So we can write this as 1 minus 1 over t. This is 1 over 1 minus t cubed. This is 1 over 1 minus t5, and so on. So we need to prove some tricky equality of formal power series. So we need to prove that if we take 1 plus t times 1 plus t squared, 1 plus t cubed, and so on, this is somehow equal to 1 over 1 minus t times 1 over 1 minus t cubed times 1 over 1 minus t to the 5th power, and so on. So what can we do here? If we want, we have two options. Either we need to make right hand side similar to the left hand side, so vice versa. But so if you want to make the denominators 1 minus t, then we can just represent 1 plus t as 1 minus t squared over 1 minus t, yes? Then we represent this as 1 minus t fourth power over 1 minus t squared. This is 1 minus this the 6th power over 1 minus t cubed power. And so if I do this for every such bracket, I will have the following product. And we see that we have, we can just make some canceling. So here, for example, so in numerator we have only even powers, and in the denominator we have all powers of t. So if we just forget about all even powers, then we can get from this guy to this guy. And so we can prove that they are actually the same formal power series, and so the number of partitions into pairwise distinct summons is the same as the partitions of only odd summons. Which is, I know if you can think of it, how can we prove it not using the formal power series? It is not very hard, but I don't think that it is very easy to construct such one-to-one correspondence, and here we can prove it just by proving that formal power series are the same. Okay, so I think we'll now take a break. I need to go and print your tests, and then in 10, like 12 minutes, we can start the test. The next time will be so-called zachot. I suppose that all students who came here, and those students who are online, I will have a decision, but I don't have it yet. But I think I will write it in Telegram. What can we do with distant students who can only be online? Okay. The same, I think, will start at 12:30, and so I think there will be like some tasks covering all the course, and so I just tried to check all your tests until Friday, and then we will have like your degree, and so which you can have by automat. But if you don't like it, you can come to the zachot and solve additional tasks, and then have higher mark. Yeah, so I think we'll have like several number of tasks, and then you just came to the 12:30, and then after you tired, you just can leave and get your mark when you can stop. So yeah, so if you have any questions, also we can discuss it into in the Telegram, or if you need some additional consultation, we can make a Zoom conference if you want. So it's not a problem. Yeah.